Yeah. Thanks, Darwin. Won't be as entertaining as Mark was, but I've got a lot of flashy videos and colour, so hopefully I keep everyone's eyes open for the next little bit. So yes, we had Heike introduce us this morning. The Optofab node is now spread around 4 universities. We also had University of Sydney there up until recent times when we did a reshuffle after the opening of the Sydney Nanoscience Hub. So at the moment we're spread around Macquarie University of Adelaide, ANU, which is quite an exciting little activity that's getting going there. So I'll talk a little bit about that at the start of the talk, and also some very niche facilities at UTS. So we're just one of the 8 nodes and we're spread across those 4 universities. You see the themes that we're sort of crossing there. It's basically making materials which work with light or making light work with us. And that's largely where the laser processing comes in. So yes, we're in Adelaide, and we've had a talk from Anna this morning, and I hope most of you will take the opportunity to go and tour the facilities here with Evan and co this afternoon. But some of the other activities within the node, and Deidre talked a little bit about this morning. Down at ANU, we're rebirthing, breathing a bit of new life into Australian precision optics. Now, that was an entity which was largely driven by CSIRO. It was hosted up in Sydney and was quite famous for preparing the optics and the coatings for LIGO, the gravity interferometric wave detectors. So CSIRO pulled the pin on that some years ago now, but there's a lot of very nice equipment that we're rebirthing down at ANU, as well as some existing facilities like this. And so just to back onto Mark and re-emphasize that, Steve is making this mill available as an ANFF tool. It's precision lathe with very accurate cutting. And at the moment, some of the other optics projects that Steve's looking at are turning aluminium mirrors for space applications. So these are little CubeSats which have sort of 8 and 10-inch mirror geometries on them. They can be beautifully turned straight from the aluminium using this facility, but also being able to make bespoke optical components like turning axicons and other sort of optics out of materials like calcium fluoride. So that's a tool which is online. And the stuff from CSIRO that I was mentioning, there was some very nice kit that's been maintained out of that. One of the key ones is the Vico, which we have there. It's a great big machine for taking great big optics and doing beautiful infrared coatings on them. But there's also a list of other equipment there which Steve is making available. So the CSIRO engineered ion-assisted E-beam sputterer and a bunch of other research sputterers which are available at ANU. So Steve will be joining us this week. We do have an exhibition booth along with ANFF in the exhibit hall. So if you want to talk a little bit more about this facility that's really gaining momentum down at ANU, try and call us Steve sometime during the conference. And also finally at UTS, there's a little niche facility there that we've brought on board. This is from the group of Igor Aronovich and his minion Blake, who does a lot of most of the work down there. At UTS, they have a real niche in growing diamond materials. So there'll be a lot of talks this week about diamond materials and NV centers and things like that. We heard a little bit from Anna this morning. But Blake is really an expert in growing all sorts of different color centers into the diamonds. So not just the nitrogen vacancy ones that everyone's familiar with, but silicon, germanium. I think there's some chrome color centers, things like that. So Blake's really developed a real ability and niche for growing that stuff. And then the other hot material that they work on UTS is HBN, hexagonal boron nitride, which are monolayer films, which are very excellent single photon emitters as well. So if anyone's working with these quantum optical materials and are struggling to get stuff done or want access to them, Blake will be a man at UTS to access that through the ANFF. So back more onto the theme of my talk, and this is the laser processing. So when people say, oh, laser cutting, laser processing, they usually get familiar with some sort of machine like this. And this is just, you know, a big laser machine from Trumpf. And again, these are fantastic technologies, but it's not really what we're talking about when we're talking about micromachining. A lot of the features that we make will generally fit well inside the spot size of the kerf of these big industrial machines. So sometimes when people come and want laser cut, we've had people come to us wanting to cut 6-inch thick silica and things like that, things that just aren't really practical. But this is not quite where we're at. We are more into looking at features which happen down here. So the sort of stuff that we make day to day sort of fits on this sort of centimeter sort of scale. Then we can step it down to features which are fairly hard to make mechanically, where we get down to this sort of sub-millimeter scale. This is some old work, but these were some little impellers for microfluidics, which were about 1 millimeter in total diameter. And then when we're really pushed to make small holes and things like that, whoops, we can get down to we can get down to sort of this sort of 5 micron region without too much trouble, and a little bit smaller than this as well, depending of if we're fabricating things with really high magnification objectives, we can get features down to sort of, 400 odd nanometers. You did see in Anna's talk this morning, the little laser shots on the piece of fiber, that was on the microstructured fiber. Each one of those little laser shots, which formed the grating on those, was about 600 nanometers in diameter. So that's sort of how small we focus down with these tools when we're really pushed to. So the facility in Macquarie, what does it look like when it's running? I just got a couple of little videos here. So basically, we're using ultra-fast lasers. They're lasers which are 10 picosecond pulse duration or shorter. Now there's a lot of femtosecond lasers around with 400 femtoseconds and shorter, and everyone's moving to those. We'll be upgrading to those sort of lasers in the next 12 to 18 months as well. But the sort of mechanics we're using is something like this at the moment. You usually have a very fast scanned laser beam and then very accurate XY tables. And the little video I've got playing here actually demonstrates the synchronization of both those motion systems, right? This is a feature called infinite field of view, where it scans the sample underneath the Gavo scanner and will continuously mark what you want to do. But just a little demonstration of the sort of hardware we work with. Again, this is what the facility looks like. I have Alex Stokes with me this week. We'll be manning an exhibition booth at the conference as well. So if any of this sort of machining stuff is interest to you, if you've got a problem you haven't been able to solve in the clean room or something like that, hopefully you can find Alex out at the conference. And this is the machine that Alex looks after a lot of our time. It's our 3D micromac machine, which houses one of these pico lasers. And the sort of work we do with this is this sort of marking. Now, this is just fun marking on silicon, but we can make a lot of different features and a lot of different materials for a lot of different applications. Let that one nearly gone through. They're quite fun. You can do all sorts of features and marking with them. So as Mark mentioned, one of the investments which we don't quite have in the country yet, hopefully by March, April next year, we'll get it on the floor. At the moment, you can see a lot of our processing is contained to sort of 2D or 2.5D. And so a lot of the applications we want to do are tube work or freeform work and things like that. So one of the items that we're bringing in is this machine, which is currently under construction in Germany. And this will actually have the extra degrees of freedom in it, which gets us more like a 5-axis mill. But instead of using the tools and bits that Mark showed you, we'll be using an ultra-fast laser. And we've got a variety of optics in the machine to deliver the laser in different ways. One of them's just scanning like we showed, but we also have a helical drilling head in there, which will actually spin and incline the beam to let us mill out all sorts of different holes in different geometries through materials and things like that. So that's where the taxpayer investment is going. The sort of things that we do with a machine like this that you don't really try and do with a mechanical mill, though Mark would have a go at this if you gave him enough time, we can do some very delicate work with the lasers because, like Mark mentioned, they're very low contact, right? We're not applying much shearing force or anything like that. So some of the really cute jobs we've done for people, and this is one that comes up fairly regularly. This is Damien Aragon over at Curtin. They use these little microarrays to do chemical separation through a glass membrane. And so they need a bunch of 25 micron pores drilled through a cover slip. So this is only 100 micron cover slip. And you can imagine by the time you've perforated this with a whole bunch of 25 micron holes, the whole thing's extremely fragile. But with a little bit of UV laser drilling, what I'm showing here, you see the texture on there, that's just some protective film protecting the glass dust from landing on the cover slip. We can do these really sort of fine sort of work, and that's the sort of stuff that we're doing day to day. And then I threw this one in. We do have a visitor here, Jason, with us this week as well. This is a piece of work that Jason has inspired. What we're showing there on the left, that's about 1 centimetre in size, and that's a slice of pyrolytic graphite. Extremely brittle material that you'd really struggle to mechanically machine. But with a bit of parameter finding and quite a few hours on the machine, Alex has machined these beautiful structures out of these pyrolytic graphite films. And so yeah, those features get down to 150, 200 micron bridges of graphite left behind. So quite really nice machining. And then applications of that sort of work when we get working with people with doing microfluidics is that we were able to, for some researchers at UNSW, machine microfluidic channels directly onto coal samples. And they were looking at the effect of infiltration of fracking chemicals and things like that through coal seams. And we're able to do it in a microfluidic test bed by having us laser machine onto graphite. So just to highlight, we work with a lot of different materials, not just optical materials. So some of the key applications in optics, though, are simple things like aperture masks. Okay, so Aperture masking really still has a place in certain optical systems. The example that I've picked on here is some work from Professor Peter Beach here at University of Adelaide, where he was designing Hartmann-Shack wavefront sensors for some of the gravity interferometers as well. So a Hartmann-Shack interferometer, the basic, it's a wavefront sensor. The basic principle is in the little diagram there. You put your laser beam onto a pattern of very mechanically precisely machined holes, and then look at the diffraction pattern that projects. And by working backwards from that, you can actually work out what the tilts and aberrations were on that wavefront. And when you're talking about these very precise interferometers, you need to know what's going on. Otherwise, you're not measuring what you think you're measuring. And so with our machines, we can machine some very beautiful arrays of just simple holes, including in materials like Invar. So Invar is a special type of metal which has negligible thermal expansion. Okay, so it'll stay the same shape and dimensions over a very high temperature range. And we can really beautifully machine those materials. The scale that we're working on here for the Shack-Hartmann wave plates, they're about 150 micron hole on a 430 micron pitch. Something like this would take Mark many hours to machine. On a laser like our machine, it might take something like 6 or 8 minutes to drill out this array of, say, between 300, 400 holes in the Hartmann plates. Sticking with aperture masks for another moment, the astronomers like this sort of stuff as well. And I like leaving this slide because it shows how creative astronomers will be with their acronyms when they think they're onto a good thing. This is for an instrument that was being tested by the University of Sydney astronomers up at Subaru in Hawaii. And you can see there the acronym they ended up with, the Visible Aperture Masking Polarimetric Interferometer for Resolving Exoplanetary Signatures, or vampires. So they got vampires out of that one. I'm showing a video here of us machining this with our older style laser, but since then we made these with the Galvo scanning as well. So these are very accurate pupil masks, right? This is dividing the optical plane of the telescope into these various channels and interfering them. And by doing that, turning the handle on the maths of that, the interferometry can give you an idea of whether a star system is likely to have exoplanets in it because of the nature of the light when you split up, the light coming from around the star. So we produced aperture masking for things like that as well. And there's a very old one. Now, this was our original work back on the AAT at Coonabarabra, and this was going back to the early 2000s when we started doing this sort of laser machining activity. And this is a slit mask. So this is a multi-object spectrograph for taking the spectra of many galaxies simultaneously. But it wasn't one where they were using optical fibers because it was working in the mid-infrared. And getting fibers that work well in the mid-infrared to run from the telescope all the way down to a spectrograph wasn't so easy to do back then. So this was actually an image passing system where the slit mask that we very accurately laser machine would define the position of all the galaxies in the field that they wanted to take a spectrum of. So, okay. Now I'm going to take a little bit of a tangent. And this is where things might get a little bit more sort of interesting and more optical orientated. One of the key academic activities that we've pursued at Macquarie for a while, and it's now, something that we can do for you under the guise of ANFF, is doing laser inscription. So this is focusing ultra-fast lasers into transparent material and inducing a change in it, which sometimes is useful, sometimes it's just pretty. And so people may be familiar with these glass type sculptures you can go and buy in a lot of gift shops and things like that. These are pretty much done in a very destructive way. Okay, there's usually a lead zirconate glass, something like that. And when you focus a really intense green laser pulse in there, you can actually create a little void in the glass. And by doing that, you can build up beautiful sculptures, and people see those around. So similar sort of principle, we're just doing it in a little bit more of a controlled way, and we're a little bit more careful about the type of materials we choose. And it looks something more like this. So this is using similar lasers to what we use for our laser micromachining. We're just delivering them in quite a different way. So these are still lasers which are nominally known as femtosecond lasers. Put the mouse on a piece of white paper, that's better. And when we're doing that, it'll look something like this. Now, the video that I've got here, this is an example of a very high numerical aperture system. You can see we're focusing with 100 times oil objective to create a really, really tight spot inside the glass. And by translating that little ball of plasma through the glass, hopefully in the right materials, we can create these optical pathways. So really, this is the pathway towards making photonic circuitry. And we end up with devices like this. We write couplers and all sorts of things. So a little bit more on this technique. You can sort of break it down into two different regimes that people play in. One will be low to mid numerical aperture focusing. So you're not focusing the laser too tight, but then you need to use some additional help. So you either need to use some beam shaping techniques because your focal geometry is going to be quite elongated unless you fix that up. Or in some materials, it can be quite useful to stack multiple modifications to form out a waveguide. Whereas the other one that we tend to explore most, because it's the most, gives you the best low loss waveguides in the right materials, is high numerical aperture focusing with much higher pulse rates. So we're talking about femtosecond pulses, but we're running the laser at megahertz repetition rates. So what we end up in the glass is essentially a point source of heat, which will cause quite an intense plasma on the glass. And we get these generally spherical looking modifications that you see here on the right. And the formation of these guys is largely driven by ion migration in the glass. And because of that, there's a lot of chemistry that you want to get right. And so this is just the one little bit of sort of research I'd share with you here. There'll be several talks from us and hopefully also from the UniSA, from David Lancaster's group, talking about this sort of stuff. But one of the things that we talk about, I've put this in here because we had glass from Anna this morning. Glasses ain't glass, right? The glass in your mobile phone screen has gone through many generations of development to get it where it is now. Our favorite playground is still in those types of glasses because they're so readily commercial in such good quality, but they all behave very differently. So what I'm showing here in the graph here on the right is exactly the same laser parameters written into four or five different, well, I've got four on there at the moment, 4 different flavors of display glass, which most people wouldn't even recognize the difference between, more or less being identical. So there's something really important in the chemistry of these glasses, which determines what you get. And really what we're chasing is something more like the top waveguide there, something which is nice and round and will have a very good index contrast. And so this is some of the work that we got out in a special edition of Advanced Functional Materials last year. This was an ANFF purpose edition of this particular journal. And the result is that we studied quite in detail the chemistry of these display glasses and what made them good for laser writing. And from that, we came up with a chemical formula or a chemical decision chart, which would lead to a designer glass for this type of process. And the result that we've got in the graph there on the right was really quite promising in that across a lot of different laser parameter space, we were able to get this glass to provide us extremely low losses. So in terms of insertion loss of an optical device, much better than the losses which are generally accepted in a commercially grown glass waveguide chip. So this is the outcome of the last sort of 5 years of ANFF-supported research, where we actually have a designer glass on the table, which is optimal for this laser writing process. Okay, so just to give you some impression, I mean, this sort of platform that I've just been through, it actually has some real world market potential. And here's a couple of companies, 2 of them offshore and 2 of them Australian, which are actually using this technique to make commercial products which are relevant to the telecom industry. Femtoprint actually uses this laser writing technique along with chemical etching to make completely, free-form channels and optical devices as well. Modular Photonics is a spin out of Macquarie. This is our colleagues. And Redshift Photonics is David Lancaster's spin out up here at UniSA. So these are all using this laser direct write technology to make these bespoke optical devices. So it really has legs and it's going to keep going. In fact, Optoscribe, you can no longer look them up as Optoscribe because they were acquired at the end of last year by Intel, who saw the technology as being extremely promising for making optical interconnects on chips and things like this. So this is it's really a good piece of technology. So just to segue into Sergio, who's going to follow me, we don't just use these for making simple waveguides. We can also use these for inscribing Bragg gratings, and I'll let Sergio take you more through it. But basically what we're looking for here is a periodic modulation of the index through an optical fiber or something like that. And in this case, what I have here is a fluoride fiber. So this is a fiber like would be made here at University of Adelaide. And this particular one is erbium doped. And so what you see when we're writing these periodic modulations, in this case, is something like this while we're doing it. So we're focusing there. The diameter of that core is about 16 microns or so. So we're magnified a fair way in. And what we're doing there is we're producing tracks through the fiber, which are about 3 micron period. So that's what it looks like here when we're doing our ultra-fast laser writing. Okay. So on that note, this is our team at Macquarie. A lot of these guys will be here during the week, so hopefully you can catch up with some of them. It's the group of Professor Mike Whitford. We have Simon Gross. Tony Fernandez has moved to David Lancaster's group, but we'll see Tony around this week. These are the guys that are the brainchild of that designer glass and a lot of the femtosecond writing. And I'll have Alex and Martin with me during the week as well. So please don't hesitate to track us down for a chat. And we are based up at Macquarie University. We do have a nice precinct up there. We're in the Australian Hearing Hub opposite Cochlear there. So if there's anything there that you think could be useful in your work, don't be scared to get in touch or track us down at our booth during the week. And that will do me. Thank you.
Ben, any questions for Ben? That was really interesting. Showcase of capabilities.
What's the rationale for moving from pico to femtosecond pulses for the micromachining applications? Is this just higher peak power? Or?
Everything really. So the lasers have come a long way in just the last 10 years. So the system that we're operating at the moment, it's a super rapid laser, which was originally from a company in Germany called Lumera. And they were building 8 to 10 picosecond lasers, very reliable, like beautifully industrial reliable systems. But they are usually only giving you 10 or 20 watts of average power. So pulse energy is up to sort of 50 microjoules and things like that. There are a couple of companies now, and one of them is Light Conversion out of Lithuania. They are now building lasers in a similar class, which have pulse durations down to 250 femtoseconds. So not as short as titanium sapphire or something like that, but still 250 femtoseconds is a pretty short pulse. So you get all of that sort of athermal processing that people like to talk about, getting beautiful edges and things like that. But light conversion has also been able to power scale those lasers to crazy power. So our new laser, we're going to go from a 10 watt picosecond laser to a 40 watt femtosecond laser. And with that, we can get up to 400 microjoule pulse energy. So in the last 10 years, there's been an order of magnitude increase in performance of these systems. The demand for that is that everything, when you're doing rapid processing with a galvo scanner, you can run everything faster, right? The process times of some of these very fine machining, that sometimes they would take 40 minutes, take hours to do something very simple. You can start to push the pace on that and start to up them. So, yeah, but shorter is generally better up to a certain point. The shorter the pulse, the more sort of athermal, the chance you have of getting a process which is very clean and athermal. Yeah.
So I have two questions. Can you do 3D printing? Or this is one thing. What's the wavelengths of the laser?
So regarding 3D printing, it depends on what sort of 3D printing you want. There are a lot of metal 3D printers which basically use the same hardware as this, right? They have an XY table and they have a galvo scanner, but largely they're used to weld titanium powder together. And when you're doing that, you don't necessarily need an expensive short pulse laser. Quite often the laser systems in those sort of 3D printers, they're often just a fiber laser, right? And you can get, a kilowatt fiber laser for very little money these days. They're very well engineered, efficient systems. So you don't necessarily need an expensive laser like that. But they are used widely, right? Like if you want to talk about 3D printing on the nanoscale, printers like the Nanoscribe are using femtosecond titanium sapphire and other lasers like that to do the 3D printing inside a polymer. So there is that. In terms of the wavelength, most of these, except for the titanium sapphire lasers, which are not used so industrially, that's 800 nanometers, and they're the most beautiful femtosecond lasers, but they're really hard to keep working well. So they're not generally used for industrial processes. In industrial processes, it's usually a 1030 nanometer laser. It's usually running off some ytterbium material. So there'll be ytterbium fiber lasers that do it. Our particular lasers are ytterbium KGW. So it's a special type of laser crystal which gives you that broad bandwidth you need to get short pulses out. And they also power scale really well. So your fundamental wavelength is generally 1030, but for the majority of the work that we do, we work at the second harmonic. So the 530 or the 515. And that's because optics work so well in the green and you have that slightly higher photon energy. So with the green wavelength, we can machine sapphire and quartz and materials like that, which at 1 micron, they're just a little bit too transparent. But by the time you machine with them green, you can actually make reasonable features in them. So that's, yeah, the wavelengths we play with.